Is that right, or does it go higher? Like straight over? No.
Oh, maybe like this was? Yes. Yes. I'm using your pocket.
Allora, facciamo, siccome adesso tra 15 secondi dovremmo andare online, magari gli disattiviamo il microfono così si vede adesso soltanto come schermata iniziale questa qua, ma non si sentono le sedie.
Sì. Come si fa di solito?
Niente, si schiaccia il bottone, questo qua.
Questo qua, ok.
Quando volete adesso è acceso.
Yes. Okay, so it's a great pleasure to have here Jason Steffen. Jason Steffen is an assistant professor at the University, at the Department of Physics and Astronomy at the University of Nevada in Los Angeles. He's deeply involved in the analysis of Kepler data and the characterization of planetary systems, in the study of the architectures. So he will tell us many things about these topics. And so thank you for being here. And maybe next seminar will be about another topic. I saw in the selected publication of your CV, a publication titled "Optimal Boarding Method for Airline Passengers." That's very interesting. So maybe next seminar.
Next time we can do one on how to board an airplane. So I'd like to thank everyone for coming. It's a pleasure to be here. I arrived last night around 2 in the morning, having just flown in, and it's good to be here. So, as was mentioned, I'm from the University of Nevada, Las Vegas, which so most people have heard of Las Vegas, but most people aren't aware that there is a university there. The most famous department at the University of Nevada, Las Vegas is the one about hotel management. But the second most favorite department there is the physics and astronomy department. So I just started in Las Vegas about 2 years ago, but over the last 10 years I've been working on the Kepler mission as a participating scientist. And so most of my funding has actually been through analysis of Kepler data. So I'll be reporting on some of the things that we've learned about planetary systems, especially compared to our solar system, from the Kepler data. A lot of this work is the work that's been done by my collaborators, of which there are many. Many of these I've been working with for almost 10 years now. I have several graduate students that I've been working with. John Bovair is going to be graduating relatively soon. And then I also have several undergraduate students that I'm working with in these investigations of other planetary systems. The theory of planet formation goes back a little while. It's been mostly unchanged since the time of Kant and Laplace, where you start with a nebula. As the cloud collapses, if there's some rotation, it will flatten into a disk, and you form the planets in that disk, and it looks exactly like this when you're finished. And with only minor changes here and there, it's actually been quite successful at explaining the overall nature of the solar system. This was back when the only known planets were the ones in the solar system. The data that we have on the planets in the solar system are actually quite good. So this is taken from the Jet Propulsion Laboratory, which monitors the positions of all the planets and keeps track of them. And you can see that there are many interesting quantities that we know to several decimal places, right? This is 7 significant figures. And we know the temperature to the part in 10 to the 2. These are quantities that we will never know for an exoplanet. Many of these, there's just no way that we can measure them on an exoplanet. And so there's only one exception, I think, and that is that the orbital period, we can measure the orbital period of exoplanets to this many digits. But that's about it. And the reason that we can measure orbital periods to this precision is because we can measure the planets in transit. So it's a reasonable question to ask, is given what we understand of the solar system and how well we understand the solar system, why bother studying other planetary systems if there's no possible way to get the same quality of data? And the response to that can be seen in the discovery of the first exoplanet that was found orbiting another star. So in the solar system formation, let me back up a little bit. So in the solar system, you have close to the sun, all of the volatile elements like methane and ammonia and water, they all are in gaseous form, and so they expand. And as they when you get far enough away from the sun, it's cold enough that they can condense into droplets. And so you form rocky cores all throughout the solar system, but the gas will accrete onto the more massive planets out where the gas lives, which is out where it can condense into droplets. So in the solar system formation, where it's hot, you form rocky planets, and where it's cool, you form gas planets. And so you can get planets that are 300 times the mass of the sun, or mass of the Earth, but mostly made out of hydrogen and helium. So this is actually one of the predictions of planet formation based upon the solar system, is that rocky planets are in close orbits to the sun and gas giants are farther away. So in 1995, this was discovered. It was a Jupiter-mass planet on a 3-day orbit, which is 1/20th of the distance from the Earth to the sun. And to borrow an exclamation from a particle physics colleague, who ordered that? So when the muon was discovered, this was Robbie's response, is like, this wasn't anything that we predicted. We wouldn't have expected to find an electron that was 200 times heavier than the one that we already have. And in this case, we have a gas giant planet that's much, much closer to the host star than the Earth is to the sun. This is not something that you'd predict from the solar system formation, and so there's clearly some other physical processes that are involved in planet formation and dynamical evolution that the solar system doesn't capture. So this is one reason to study exoplanets. Another reason to study exoplanets is that right now we have nearly 2,000 confirmed planets orbiting other stars. And we have almost another 5,000 that are very likely to be planets orbiting other stars. Maybe 90% or 95% of these planet candidates are actually real planets as well. And so you almost have, for every planet in the solar system, 1,000 other objects. And it turns out that the vast majority of these planets are also ones that you would not predict from models of the formation of the solar system. Most of these planets that have been discovered so far don't look anything like the planets in the solar system. They're slightly larger than the Earth, but they're smaller than Neptune. They have some atmosphere, but not very much, and they orbit closer to anyway, so a lot of their properties are very different from the planets in the solar system. So when we want to understand planet formation in general, there are two directions that we can look at it. We can come in from the left and look at the properties of individual planets. So we take a planet, we study its atmosphere, we study its mass and what its composition might be. At the same time, we can get some insights into planet formation by coming in from the right, where we look at the properties of the whole system, like all of the planets in the system, where they live with respect to each other, how their masses relate to each other, and how those relate to the host star. So many people are focused on planet properties themselves, the individual planets, and understanding individual planets as a clue to the formation of the systems. My interest is actually over here in studying the properties of the whole system and how the whole system, or what the whole system can tell us about the dynamical processes that are going on. My preferred method of finding planets is through transits. And that is when you have a planet that passes in front of the star. So this gives you the flux or the brightness of the star as a function of time. And when the planet transits in front or passes in front, then the star gets dimmer briefly. And if you add all these together, you get this curve. And there are a lot of things you can learn from this, the shape of this curve. You can tell, for example, if the planet passes up here, or if it passes through the middle, based upon the shape of this curve. You can tell the planet's size relative to the star based upon how deep this is. So Jupiter is 1/10 the size of the sun, so if Jupiter transits, it blocks about 1% of the light from the star. You can very well measure the orbital period, because that's just the separation between each of these dips in the light curve. So the data up here in green, this is just looking as the planet goes behind to see if you can see reflected light. So you can actually observe with the data are so good from Kepler that you can observe the phases of the planet as it goes around. You can see the reflected part of the light coming from the planet. You can actually see the fact that the planet changes the shape of the star and turns it into an ellipsoid, and then so you get changing cross-section. You can also see the fact that the planet, as the planet orbits, the star moves towards and away from you and gets brighter from Doppler boosting from the orbit of the planet. So these are, for the brightest stars, Kepler data are in many regards better than data that we even have for the sun. In terms, you can measure oscillations of stars, a whole bunch of different oscillation modes. It's actually quite impressive what Kepler's been able to do. And it's a very sensitive thermometer and can measure very easily temperature fluctuations that happen when it changes its orientation. So this is one method of finding planets. It's not the only method. And it actually, a nice thing about most planet detection methods is that they complement each other. There are few planet detection methods that actually overlap that much. For example, Gaia, planetary transits only measure the properties of the planet as it passes in front of the star, and you only get the size. If you measure, there are other ways where you can measure the mass, but not the size. And so you combine them and you can get both the mass and the size. With some methods like the Doppler shift method, you can only measure the projected mass. So if you have a system that's slightly tilted, then you can't actually measure the mass of the planet itself. But if you combine that with Gaia information or astrometric information, then you can reproduce the three-dimensional orbit. And so transits, astrometry, and Doppler measurements, radial velocity measurements, combine in a unique way to actually constrain the entire orbit of the planet. I would argue that's not really a common thing to have different techniques that can completely independently measure or combine to fully characterize the system. Some of the value of transiting planets, you can measure the orbital inclination, which allows you to determine the mass of the planet. You can measure the planet size, as I mentioned. You can measure the orbital phase to about 100 parts per million. So where it is in its orbit. And this actually, so this is about 100 or 1,000 times more precisely than you can measure the orbital phase from Doppler shift measurements. And the reason is that the transit signal is such a narrow signal that you can pinpoint the orbit. Yeah?
Okay, so with the transits you can measure the ratio, the size of the planet with respect to the star.
Right.
But how does the orbital inclination give you the mass of the planet?
It allows you to get the mass of the planet because it removes the possibility of, it tells you the inclination of the planet with respect to the line of sight, and then you can use that with either the Doppler shift measurements. You have to have another, yeah. So, and now Doppler shift measurements aren't the only way to do this, and I'll show that, but it's the most common way. The precision of this orbital phase, the fact that we can measure it this well, gives rise to new dynamical processes that we can actually study in transiting systems that we can't study, or it's very difficult to study in other systems.
So that precision just with 4 years of Kepler, not K2 or...
Right. But this actually, from one orbit to the next.
Okay.
So for each individual orbit of a transiting planet, you can usually measure the orbital phase to that precision. So it's actually interesting because with a transiting planet, you can measure what's called the orbital obliquity, which is the angle between the orbit of the planet and the spin of the star. So, and briefly, if you have a spinning star, then you have one side of the star that is blue shifted and one side of the star that is red shifted. And when the planet passes across that, you actually can see an anomalous, so you block the blue shifted side, that gives you an anomalous red shift, and then you block the red shifted side and that gives you an anomalous blue shift in the spectrum. And you can use that to tell, for example, if the planet is orbiting in the opposite direction, because in that case you get the blue shift and the red shifted sides are switched. You need spectroscopic data, but you can't do it at all if you don't have a transiting planet. So combined, that's one of the beauty of the field, is that with combined measurements you can really characterize things. And it turns out that many of the hot Jupiter, there's been a few hundred hot Jupiters discovered, and a significant fraction, is like 20% or 30%, have very highly inclined orbits, and several that are retrograde. It's not uncommon to see a planet orbiting backwards with respect to the spin of the star.
When you say that we measure the planet size, but this depends on our knowledge of
The star.
the star.
Yep.
Are they known?
So,
Excellent.
typically what's done is that we use stellar models to give the size of the star, and the best that usually can do is 10% or 20% or 10%. However, with Kepler data, you can use astroseismology measurements to get the density of the stars to much, much higher precision, and therefore their size. And with Gaia data, we expect that we can get many, like hundreds of these, the properties of the star of hundreds of stars in the Kepler field of view to a few percent, and therefore the planet radius to a few percent. So, anyways, we appreciate all the people who study galactic structure for providing good exoplanet data to understand the properties of the star. And I think this is fair to say that most of our uncertainty in planetary properties stem from uncertainty in the stellar properties. So that's our largest source of systematic error, is the stellar properties. So the Kepler mission looks like this. The mirror is about 1.5 meters across. The aperture is about 1 meter across. The company that put it together is Ball Aerospace, and they used to make jars to can food when you'd like put food in the jars and seal them up. So this, it's the same company. They do food canning and aerospace. The field of view is in the summer sky. It's in the constellation of Cygnus and Lyra. It's about the size, it's 100 square degrees. It's 10 degrees on a side. So it's about the size of the palm of your hand when your hand is extended at arm's length. One of the things you can do with transiting planets, this was my dissertation topic just a couple years ago, is called transit timing variations. What happens is if you have a planet that's orbiting a star and it's by itself, if you have just one isolated planet, then the transit times are equally spaced. But when you add a second planet into the system, then the transit times are no longer equally spaced. The gravitational interaction between the planets will cause the time interval between the transits to vary. And you can use those transit timing variations, or TTV. So that's my largest contribution to the field of exoplanets, was shortening transit timing variations to TTV, the acronym. And it's all been downhill from there. I'm hoping to have something equally valuable before I retire. So transit timing variations, and these were discovered in 2 independent but basically simultaneous papers in 2005 with my advisor and myself. This was my first paper in the field of exoplanets, was understanding the nature of these TTVs. And there are many different ways of producing them. So this is an example of what it looks like. These are measured, so these are, the straight line here is what you would get with a constant orbital period. So this is if there's no perturbations, the planet has a constant orbit. So these deviations are the arrival times of the transit times as measured from a constant orbital period. These are real data taken from Kepler. This is the Kepler 18 system, if that matters to you. It's KOI 137. So these are the measured transit times of the inner planet and the outer planet, and you can see that the deviations are about 15 minutes. Like sometimes the orbit is 15 minutes shorter than at other times. And the typical uncertainty is a few minutes with Kepler data. This is not the largest deviations from a constant period. There are some planets whose orbital periods change by as much as 2 days from one time to the other. So you can imagine a planet on a 30-day orbit whose orbital period changes by almost 10%. That would be like if every decade we had to have a month shorter or a month longer year, is how much some of these planets change with respect to a constant orbital period. So this is what these deviations look like. There are many systems, you know, a few hundred systems that have measurable transit timing variations. They were used to discover many planets. So we could use transit timing variations as a way to confirm that these planets were orbiting the same system, because when one planet's orbit gets longer, the other one gets shorter to conserve energy. And so for a long time, for several years, this was the primary way that Kepler was able to take a planet candidate and declare that it was a planet, was because you could see these orbital interactions. And so there were several papers that produced all of the green planets in these systems that moved them from candidates to planets. Kepler's discovered a fairly wide variety, and also in exoplanet systems in general, there's a fairly wide variety. For example, this picture is the Kepler 11 system. There are 6 planets in that system. The outermost planet has an orbital period that's around that of Mercury. So it has 6 planets all basically inside the orbit of Mercury. The total mass is like 30 Earth masses worth of planets. So it's more than what we have in the solar system, all inside the orbit of Mercury, in this one system. There's no viewpoint from our own solar system where you can see 6 planets transiting the sun. So no observer in the universe can see this many planets in our solar system. We have another example here. This is the Kepler 36 system. These are 2 planets whose orbital separation is only 10% different. So you have one orbiting at 11 days and one orbiting at 13 days. And the semi-major axis difference is less than 10%. And the difference is that the inner planet is rocky and has a density of about 8 grams per cubic centimeter. The outer planet is gaseous and has a density about 1 gram per cubic centimeter. So there's almost a factor of 8 difference in density, even though they're separated by only 10% different in their orbital spacing. They're very close to the 8 to 7 mean motion resonance, so where one orbits 8 times and the other one orbits 7 times. And so this is another, I mean, all of these are different kinds of systems that Kepler have discovered that require some explanation in a general theory of planet formation. We've discovered, I think, about 11 circumbinary planets. So most planets, or most stars in the sky are in multi-star systems. So the famous phrase is that 3 out of every 2 stars in the sky is in a binary. And so we've discovered, we already knew about planets orbiting one star with a distant binary companion. That had been seen before. We have discovered in Kepler systems of a binary star system where there's planets orbiting both stars. And we've also seen with Kepler the first definitive discoveries of a binary star system where there's a planet orbiting the whole binary. So there have been about 11, I think, circumbinary planets that have been discovered by Kepler. Mm-hmm.
Those are strictly unique, or there are ambiguities? I mean, when you have many parameters, different planets, you can possibly imagine that in a limited time, different structures of the systems would produce the same.
Right. So in this case, in the case of the circumbinary planets, the orbits are quite well constrained of all the bodies, because in many cases the stars will eclipse each other, and then you have the planets eclipsing both of the stars as well. And so when you do a dynamical model, it really constrains what are the allowed orbital periods and so forth. So for the ones that have been discovered, they're quite well characterized. I think anyone who studies them has no doubt that there are many that we're missing, because it's just hard to say, okay, this is a circumbinary planet because we have one small data point that's off. It actually takes a fortuitous data series that has the transits that you need in order to characterize the system. So there are many that are missing. Another thing that's challenging with circumbinary planets is that when you're just finding planets orbiting an isolated star, the transit shape is usually about the same. The orbital period, even if there's transit timing variations, the orbital period is roughly the same. And so there's certain algorithms, like detection algorithms, that allow you to find planets orbiting a single star. It's much more difficult to find planets with an automated pipeline around a binary star, because every time there's a transit, the stars are in a different location, and there's no regular signal. It's a completely unique signal almost, which makes it difficult to then train a computer to do it in an automated fashion. I mentioned before, we've discovered hundreds of hot Jupiters, planets that shouldn't be there by solar system standards. And there are also a lot of planets that have highly eccentric orbits. So this is HD 80606, which has an orbit eccentricity of 0.95. And it's the outermost part of its orbit, it's near to the Earth. The innermost part of the orbit, it's a 20th the distance from the Earth to the Sun. So finding things like this, none of these are like the solar system. None of these planetary systems are like the solar system. If we take a look, for example, at systems with hot Jupiter, so this is the planet mass on this axis and orbital period on this axis, and you can see that there's this cluster of points here at about 1 Jupiter mass and 3-day orbital periods. So this population of hot Jupiters, they're hard to form in situ. It's very difficult to form a Jupiter mass planet that close to the host star because there's no material, there's no volatile material there. And so you have to have some kind of migration. They have to form, we believe they have to form farther out and come in somehow, come in close to the host star. And there's a couple ways to do this. We've seen it in the solar system, evidence of migration. So for example, in the solar system, it's very difficult to form Neptune at Neptune's orbit before the disk dissipates. So Neptune, the disk dissipates in like 10 million years, and if it takes 20 million years to form Neptune at its current location, then you run out of problem that there's no more material to build the planet with. So the one way to solve this is if Neptune forms closer to the Sun so that it can form in time and then moves outwards, we can get it to its current location. If that's true, if it did happen that Neptune formed closer in and then moved outwards, we should expect some dynamical signature of that in the small bodies in the solar system. So these are basically the comets in the outer solar system. So these are the location of ice bodies, like Pluto is an example. They're trans-Neptunian objects. And so these form a disk, kind of like or they're in a belt similar to the asteroid belt, but they're made out of ices. If you move one object with respect to another, you can capture them into specific orbits. They can become trapped into specific orbits. And that's shown here with these ones here that are marked in blue. These are objects that are in mean motion resonance with Neptune. For example, this group here orbits twice every time, they orbit once every time Neptune orbits twice. This group here orbits twice every time Neptune orbits 3 times. Pluto is an example of one of these objects. So Pluto is in a mean motion resonance with Neptune, and that's strong evidence that Neptune actually moved outwards and swept these things into these particular orbits. There are also some Neptune Trojans, objects that are trapped in the actual orbit of Neptune and orbit near the Lagrange points. That basically what happens is when you have differential migration, as the orbital distance shrinks, once they capture into that resonance, then they'll stay in that resonance forever, unless there's something else that breaks it later on. And so looking for, if hot Jupiters did form farther out, we can look for objects near mean motion resonance as evidence of how they moved. But this isn't the only way that you can move something. So if you move it in a gas disk like this, then you might expect them to be trapped, expect small objects to be trapped in resonance. However, if you produce hot Jupiters by having scattering events where 2 planets come close together and one gets ejected, and that puts the second planet on an elliptical orbit, that orbit can circularize through tides. You basically dump the energy of the orbit into the temperature of the planet and the star. You heat up the planet and the star, and then you shrink the orbit through this tidal friction, conserving angular momentum. So you can either start in a gas disk and move things slowly and potentially capture objects into resonance, or you can start with several large objects, remove them, and then have an elliptical orbit that slowly circularizes over time. So these are two competing methods of forming hot Jupiters. If you look at 63 hot Jupiter systems from Kepler, so this was a study that I did several years ago, if objects come close to mean motion resonance, if they move in slowly and capture into mean motion resonance, then you should see transit timing variations, because that's where the transit timing variations are the largest. And it turns out, if you look at these, the hot Jupiters from Kepler, there are no examples of transit timing variations that you see in any of these systems. And so there was no evidence for additional transiting planets. There's no evidence for transit timing variations. There's no evidence for having an inclined perturber or having another planet with a perturbing hot Jupiter that we don't happen to see. So this strongly favors models where you have planet scattering or some other exotic dynamics that puts Jupiter-mass planets on highly elliptical orbits that then circularize through tides. So far, there's only one example of a system that is different. There's only one example of a system that has small nearby companions, and that was discovered in the K2 mission. So 1 out of 100 planetary systems could have formed through the disk migration, at least as far as we know it at this point. So that particular system is WASP-47 for those who study these things. There's no evidence for small planets. And yet, when we look at the small planets in similar orbits, small planets on 3-day orbits, we see all of these things. We see transit timing variations, we see additional companions. It's just the hot Jupiters that are isolated. So that points to one constraint that we can place on the history of these planetary systems. So hot Jupiters are lonely, and that's an indication of a troubled past. Yeah?
Could it be though, I mean, these things are so close to their host star that any planets inside those hot Jupiters would have been pushed into the star. And so that's why we don't see them.
So that's one possibility, although this one particular system actually has a small planet interior to the orbit. So it's a hot Jupiter on a 4-day orbit. It has one planet interior at slightly less than a day, and it has one planet exterior that's near the 2-to-1 mean motion resonance. It's actually slightly wider for some unknown reason. But so the orbits are stable until you get really close to the host star. Part of the issue is that not everything needs to trap into interior orbits. Smaller planets actually tend to migrate faster than larger ones. And so if you have something moving in slowly and you form anything behind it, they will cascade inwards and capture into exterior resonances. So all it takes is a difference in their migration rates to produce the capture. It doesn't have to be on a particular side. So here's an example. This shows planet radius on this axis and orbital period on this axis. You'll see this. You've seen this figure before, and you'll probably see it again. The hot Jupiters are these ones up here, which is a small fraction of all the planets that Kepler has seen. It's about 1% of all the planets that Kepler has seen. And so I'm also, while it's fun to study individual systems, most of the planets are not like hot Jupiters. And so I want to understand more about how these systems live, what their histories are like. And by the same token, if there's a lot of migration in these planets, then we should expect them to be near mean motion resonance. One thing you'll notice about these planets is that the majority of them are larger than the Earth. So here's one Earth radius, and smaller than Neptune. Neptune is 4 Earth radii, so that's right here. So most things seem to live here in a regime where there's no objects in the solar system of that size. If you look at the distribution of orbital period ratios, so this is where we might expect to find planets near mean motion resonance. So if you look at orbital period ratios of these planets, you find that indeed there are features near first order mean motion resonance. So there's been, in many cases, there's clear evidence for planet migration. Another thing that you see here is that most planet pairs are not near mean motion resonance. While there are some near the 3 to 2 or near the 2 to 1, most of them are sitting out here. And if you correct this, so this is a distribution that's just the raw information. If you correct it for the fact that it's easier to find planets that are closer together, and it's harder to find them as they get farther apart, you get a different graph. You get this one, okay, so this is a little bit messy. The blue curve is the interesting one. And the blue curve corrects for, it takes the observed distribution of orbital period ratios and corrects for the fact that it's easier to find planets that are closer together, it's easier to find planets that are closer to the star, for a number of reasons. One is that the geometry allows more planets to transit, and the other one is that when you get more transits, you're more likely to see it in the automated pipeline. So it corrects for both the pipeline completeness and for the geometric issues. So this is basically the same graph as this, except things have been smoothed out with a kernel density estimator. Some interesting things to take away from this figure, and it's this part of the graph that I find most interesting. What's out here is, some of this is noise, but a lot of this is not noise. These are the peaks near the 2 to 1, the 3 to 2, 4 to 3, 5 to 4, 6 to 5, 7 to 6. Okay? And this one, the most prominent feature is not near any of these mean motion resonances. And this feature keeps turning up with almost every other new planet discovery in an existing system puts another planet in this peak, not near the 2 to 1. And so I have some students that are working on trying to understand what's the origin, like why is this 2.2, why is that a thing? Just to give you an example, this one planet, this one planetary system, the hot Jupiter with other planets nearby, WASP 47, you have a hot Jupiter and it has an outer companion in this peak. So one possible way to do this is through the interactions of planets and the disk. When you have, so this is a disk, this is the whole disk, and then it's been folded. So this goes from 0 to 2 pi, and then this is the radial distance. So this is the whole disk, but put onto a rectangular coordinate system. When you put planets in the disk, you can see that the planets create wakes. So when you have small planets, they can interact with these wakes. You can have a fairly strong wake in between them, and that might cause the planets, it might affect the planet's motion. So we're doing some investigation into this. That it could be that the wakes of one planet are preventing another planet from getting too close to it. On the other hand, if you have more massive planets, so this is Jupiter mass planets, they empty out or they drain, they open up a gap in the disk, which means that you have much weaker wakes that don't cause, the planets no longer have to interact with. I mean, they're too weak for the planets to be affected by them. So this is one thing that we're investigating. One possible explanation for this strange pileup is that if you produce a wake, maybe that wake shocks into the disk and then that deposits angular momentum and prevents planets from forming. Anyways, this is a work in progress. We're trying to understand where this comes from. We've seen it happen. We want to understand what are the bounds of planet properties and disk properties that can cause this.
Sorry, but
Yeah.
this ratio of 2.2
Mm-hmm.
depends on the mass of the planet also? Or?
No, it doesn't. Okay, so it doesn't seem to depend on the size of the planets in the Kepler data. I can't say if it depends on the mass of the planets in the Doppler measurements, because Doppler measurements also do this. Most Doppler measurements the Doppler measurements for most systems actually have a hard time distinguishing planets with orbital periods that are this close together. So it may show up in gas giants, but it's hard to tell. Another feature, and what I've been looking at, most of my work has been trying to identify things that require explanation. So why are hot Jupiters by themselves and isolated? Why is there a large pileup of planets at some orbital period ratio that you wouldn't expect? Another thing that I wanted to look into is how does the structure of a system change with the size of the system? Because dynamics, like planetary dynamics, it all scales with the semi-major axis. So there's no preferred, it's not like a system of planets that's close to the star is really different than a system of planets that's far from the star if their orbital period ratios are the same. It's the ratios of distances that matter in dynamics, like in Newton's laws. It's not the absolute value of these things that matter. And so the only time that you would expect the structure of a system to change is if there's some new physics that you have to include in the model that affects the structure. Maybe if you get very close to the host star, tides will turn on, and that's not point mass particles going in Keplerian orbits anymore. Or maybe if you get very far from the star, then you run into issues where the disk gets truncated or something like that. So if you have differences in the architectures of the system as a function of size, then that can lead you towards other physical effects that affect planet formation. So this shows the orbital period ratio as a function of the inner planet's orbital period. So this, the 2 to 1 would be here, 3 to 2 is there, the 3 to 1 is here. And what we found is that once you get inside a couple of days, planets become more widely separated. That you can have planet pairs that are very close together. I mean, this is like the 7 to 6 mean motion resonance. You can have planet pairs that are very close together. So this one right here is the 7 to 6 mean motion resonance. So that's the Kepler 36. You can have them very close together here, but once you get inside one day, then you're talking about separations that are, 5 to 1 or so. So these are much more dynamically spaced than planets that are farther out. And so there's probably something going on here. There's actually one exception to this wedge of missing planet pairs. And okay, so there's 2 exceptions. But these 2 exceptions are in the same system. These 2 planet pairs, so this is a 3-planet system, so you have 2 period ratios, and that's orbiting a star that's 0.1 solar masses. It's the smallest, well, it used to be the smallest, now it's the second smallest mass. It's the planetary system orbiting the second smallest star where they've been discovered. TRAPPIST, the one that came out a few weeks ago, is less massive than this. But otherwise, this is a very low mass star that has planet pairs, these very close planets in it. So,
Sorry, but at a certain point, at this left corner, you will have unstable orbits, or
it turns out, so only about a month ago, there was a paper that was published that I think gives the right explanation for this. And that is that once you get this close to the star, then the tides will cause the inner planet's orbit to shrink over time. And so it's unstable over very, very long time scales, but longer than the age of the systems. So that's a paper by Eve Lee. And I think she has the right, or at least so far the best explanation for why this planets become more widely separated. But until a few weeks ago, there was really no explanation for this. Just to give you some sense of scale, so these 2 planet pairs, so this is a 3-planet system with 2 planet pairs. It looks like this. So here's Jupiter and its 4 moons, the 4 large moons. And here's Kepler 42 and its 3 planets. Everything is to scale on this. The only thing in this that's not to scale is the distance between Kepler 42 and Jupiter. But everything else is the right size and orbital distance. So these are very close to their host star, and the host star is not very massive. And this is a sense of the scale. So this is the outermost planet in that system compared to Mercury.
So those planets around Earth are very, very small.
They're very small. Yeah, they're like Earth size and smaller. Yeah. So there are a lot of things, what are kind of physics beyond the standard model, that could be going on with these short orbital periods. It could be general relativity that causes the orbits to, as the orbits evolve, general relativity causes the precession, which then breaks some kind of motion, or that can affect the motion of the inner planet more than the outer ones. You can have tides, which I think is the most plausible explanation so far. You can also have, it could be something with the magnetic field interacting with the disk from which everything formed that causes, difference in dynamics. All of these are beyond, these aren't Newton's laws anymore. You have to add something else. Another thing that I'm looking at is different planet populations. If you look at the systems from Kepler that have multiple planets in them, so these are ones where you have multiple planets transiting the host star, and you compare it to ones where there's only a single planet transiting the host star, these don't look quite the same. They're similar. They have, they're all concentrated near 10 days and 3 Earth radii. But the singles, for example, have hot Jupiters, which we already know hot Jupiters are isolated, and the multi-planet systems don't have any hot Jupiters. If you try to reproduce this distribution from this distribution, say if they're actually the same, then these should look the same. I should be able to draw from this sample and reproduce this sample. It turns out that you can't do it. There are places that you miss. You miss the hot Jupiters, you miss planets on very wide orbits, which makes sense because you see the inner planet and the outer ones don't land in the Kepler time series. But you also see a large excess of single planets on one-day orbits, Earth-sized planets on one-day orbits. And when you look at the numbers, there are something like 150 one Earth-sized planet, one-day orbit objects that require explanation. Some of them are probably false positives, like eclipsing stellar binaries or something like that. So we did a budget for where do these come from. If we start with 150, how many of them are false positives? How many of them are spurious detections? How many of them are real Kepler multi-planet systems like Kepler 42, but happen to be inclined so that you don't see the outer planets or something like that? So we did a budget for this, and we found that at least 1 out of 6, and perhaps as much as half of them, are have some non-standard dynamical history, that they're not the same kinds of planetary systems as the rest of them. The best example I can come up with is, if I go back briefly, keep going, is when you have a system like this. So you have a pair of planets with a one-day orbit for the inner one, but the outer one is at 30 days or at 50 days. So those are planet pairs that are dynamically very widely separated and where there's nothing in between them. So something like that could be the source of these isolated single hot Earth systems, is that you do have an object here and you have a companion that's much farther away, but it's much, much farther away than anything in the solar system. Right? The widest separation we have in the solar system is a factor of 6, and that's between Mars and Jupiter. Okay, their orbital period ratio is 6:1. This separation is equivalent to the separation of Earth and Saturn, or Earth and Neptune. So these are very widely separated planets. And that's one of the possible explanations for where we get these extra hot Earths, and that would imply some difference in their dynamical histories. So in the end, what we've learned from Kepler that we can use to inform planet formation models is that hot Jupiters are lonely. They're isolated. They most likely, or at least most of the time, have some exotic dynamics that put them on eccentric orbits that then circularize. Most systems are consistent with high multiplicity planets. So most planetary systems have multiple planets in them. And we just happen to miss some because they don't transit. Most planet pairs are not near mean motion resonance. So migration, while it may play a role, is not so dominant that everything gets captured into mean motion resonance. And some planet pairs are near mean motion resonance, and some of those are very close together. And so somehow, in several of these systems, you have to bring planets close together without them going unstable and stop them. Which, I mean, you can come up with a model for an individual system, but now you have many that you have to grapple with. There's evidence for physics beyond the standard model as you get to shorter and shorter orbital periods. And it seems as though tides is one of the main contributors to this. And there seems to be a significant excess of planet pairs near a period ratio of 2.2, unlike things that you would predict. And that many of these hot Earth systems have a unique history that's separated these hot Earths from their nearby companions. All of these things. Mm-hmm.
What do you think about the perspectives in future for testing?
I think right now, the issue right now is the lack of the theory. Like, I don't think anyone has sat down and said, what effect does general relativity have on planet spacing at these close orbital distances? So right now there's no theory to test. The material, the tools are there to derive, like to come up with the theory, but I don't think anyone has put the time into it. So the thing from Eve Lee, her study, does make predictions, and so those ones presumably could be tested with new test data. I don't know that there's a whole lot that can be done with Kepler data. Okay, I'd have to look and see, like, what are her specific predictions and how does that relate to what we observe. But the TESS data, so TESS is the next mission, will find many, many objects similar to this that can serve as an independent like measurement of those consequences. So if you're a theorist and want to crank on some of these magnetic field things and general relativity, that kind of stuff, I don't think the theory's been fully fleshed out and vetted in the literature to the point where there's a reliable test that you can do on them.
Just a comment about the fact that planetary migration can have played an important role also in our solar system.
Mm-hmm.
And you were mentioning the case of Neptune.
Mm-hmm.
There's also another indirect evidence, and this is the small mass of Mars.
Mm-hmm.
Because according to the classical growing planetesimal models and so on, it's difficult to stop Mars to have a larger mass.
Right.
And according to the most modern models of solar system origin, this can be explained by an Earth migration of Jupiter
Mm-hmm.
toward the short geocentric distances that was sufficient to perturb the planetesimals in the inner system in such a way that Mars would not have the bricks.
Right.
And then according to this model, it's called the Grand Tech.
Mm-hmm.
Jupiter came back when a situation of resonance with Jupiter and resettled was reached. And then this is called the Grand Tech just because you have a migration that then goes back.
Right. So this is understanding the size of Mars. So Mars is too small and Neptune was too big. And it turns out that there's a migration explanation for both why Mars is small and Neptune is big. So Neptune being big, that's the Nice model, is like you have these things, they form, and then the system kind of relaxes. And as it relaxes, once you dissipate the disk, then you go from a damped system to an undamped system, and it relaxes into its new steady state, or quasi-steady state. The Grand TAC model, which came out in 2012, it's like a decade after the Nice model, was put in to explain the size of Mars. Why is Mars so small? So this is Kevin Walsh and Alessandro Morbidelli, and others. And and what you say is correct, that they hypothesized that Jupiter probably migrated inwards. If Jupiter migrates inwards, it will truncate the disk, it will scatter the planetesimals, and reduce the material from which you can form Mars. And because Saturn is smaller, it migrates faster. And so as Saturn comes in, it hits a mean motion resonance, and then the differences in the torques that you get from a less massive outer planet will pull Jupiter back out of the inner solar system. And so in that model, my understanding is, I have to reread it to be particularly specific, but I believe that it's the 3-2 that they find is the one that's most likely to bring them back out. And then as the system relaxes, comes back into equilibrium, that it breaks that resonance, and then Saturn migrates outwards until it gets near the 5-2, which is where it is today. So that's two pieces of evidence for migration in the solar system. I think the Grand Tech model has a lot of circumstantial evidence to support it, but it doesn't have it's not yet at the point where it has the convincing evidence that Neptune's migration does. Because Neptune, I mean, you can measure these things near mean motion resonance. The Grand Tech model is a theory that was put forward to explain the mass of Mars. And I think, I mean, it should leave other signatures that we can study in more detail. Yeah, Grand Tech is first, and then Nice model is second. Yep. Yep. One more question?
What's your opinion about these theoretical models that foresee formation of planetary system, compact planetary systems of super Earth, of 4 to 5 super Earth, in situ? So they may form by inward migration of solid materials, like metals, or do you think they can form in situ, or they?
So there are a number of people who have studied, so Brad Hansen and Scott Tremaine. I mean, these are pretty bright people that are looking at in situ formation as the dominant mechanism to form super Earth systems that are close together. Now, close together has not been clearly defined. It's not been well defined because the orbital spacings, the orbital period ratios of these systems are not dissimilar to the solar system. You know, Jupiter, or the Earth and Neptune, or I'm sorry, the Earth and Venus are near the 3-2, which is where most of these systems are too. So it's not like, dynamically speaking, these are much more compact than the solar system. The difference is that it's more material closer in to the host star. And so my suspicion is it's a combination, that any mechanism that's allowed actually happens, and it's our job as observers to find out how frequently the different mechanisms happen. To me, this is an exciting time to be in exoplanets because we've gone past the discovery phase of I found the 7th planet. It's no longer a bug collection. It's now we have a sample that's been systematically studied or systematically analyzed, and we can gain, the kind of physics the kind of science that I like to do is where you have a statistical sample and you can identify certain populations that require explanation, and you can use that to actually hone a general theory and say, you start with a distribution of disk masses and sizes and compositions, and somehow you have to produce this many hot Jupiters, this many close compact systems, this many solar systems, this many gas giants, this many planets near the 2-to-1, this many planets near 2.2. You have to separate them out. The particle physicist in me likes that kind of predictive theory, and I think we're getting into the phase now where we've gone past the here's individual systems to here's sets of systems that have all been studied systematically to identify anomalies. And anyways, to me it's an exciting time to be there. I view it as this is kind of where cosmology was in the late 1970s. And it's where particle physics was in the late 1960s. And there's a lot I think that we're going to learn in the coming decades about planetary systems because we have the data to drive the theory. Yeah. So there are a few observations that have been made relating host star properties to planetary system properties. Like, it seems to be that the more metals a star has, the more you're more likely to find a Jupiter mass planet. Like, hot Jupiters tend to be around more metal-rich stars. The implication would be that, especially if hot Jupiters form from planet-planet scattering, that the more metals there are, the quicker you can form cores and the faster you can produce multiple planets. And then those planets can scatter off of each other, where if you don't have enough metals, it takes longer to make them, and so you don't get as many. There's evidence that for smaller mass planets, you get more small objects, but this is not, so these measurements, we can say things like out to 50 days, smaller mass stars have more planets and they're smaller planets. But 50 days to a star that's half a solar mass is very different than 50 days to a star that's twice a solar mass. And it's not clear what the right unit is to measure, because orbital period is somewhat arbitrary, right? That has to do with like the Earth's rotation. There's some physical distance that means something, like naturally means something, that might help us understand better why planets form the way they do around smaller stars and around larger stars. So we know that there's differences, but it's not clear that those differences aren't well explained in terms of like the stellar properties, how long the disk is around, what kind of materials can survive for the duration of that. When you do the integrated X-ray flux from a M dwarf star, it's more than, so all of these things, I think that there's going to be something that comes out of this that allows us to say, okay, these systems are equivalent. This M dwarf system is equivalent to a G dwarf system with these properties, and that will help kind of figure out what the real difference is between these systems. But I don't think it hasn't been done yet. It's more than just thinking. I'm pretty sure that that kind of detail hasn't been done yet, because it's very hard. You have to, there could be a lot of ingredients that go into it that we don't fully understand. Okay. Uh-huh.
It's about these hot Earth systems,
Uh-huh.
ultra short period planets. Do you think they are rocky planets that were scattered inward, or they were bigger planets that lost their atmospheres because of the XUV flux, stellar flux?
So so there are several models to explain hot isolated super Earths. One of them is that they could be leftover cores from hot Jupiters, that the hot Jupiter gets very close, and then Roche lobe overflow causes so the X-ray flux I don't think is enough. It's not enough I don't think there's enough to evaporate the planet's atmosphere. But Roche lobe overflow is viable. It's a way where you can strip off hundreds of Earth masses worth of stuff in the lifetime of the system. So it's a possibility. It's not obvious that that's the main channel, like the main formation channel. So I don't think it's been excluded, but I kind of doubt that it's the primary driver. Now, you could have a Neptune-sized planet. You could have a smaller-sized planet that has its atmosphere stripped off, but a Jupiter is much harder to do. So there have been some proposals that maybe these are like miniature Neptunes that have had the atmosphere stripped off, and I think that's a possibility as well. It shows up in the transit data that there's a gap between small objects. There's no 3 Earth radius objects that are at 1 day. You either have gas giants at 3 days, or you have rocky planets at 1 day, and anything in the middle could have been stripped off through some mechanism. So that's a viable thing, and you could have a small planet that's had its atmosphere evaporated off, because it only takes like 2% of your mass to be in the atmosphere to get 3 Earth radii, and the atmospheres are very tenuous for some of these planets. But for a Jupiter, I mean, it's a different pressure that's supporting it. There's a lot of, the atmosphere is much more tightly bound to a Jupiter than it is to a Neptune. I think that if we can explain the period ratios where there's like 20 to 1, where you have one planet on 1 day orbit and then the other one's on 20 or 40 or 60 day orbit, that is probably the majority of the hot isolated Earths, is because for every one of those that we see, there's something like 10 or 15 that we miss. And when you just do the ratios, that explains the majority of the ones that we observe. That would explain the majority of the ones we observe. So my suspicion is that if a mechanism is viable, then it happens. And then the question becomes, how often does each one happen? So, all right. Thank you, everyone, for your...
Thank you.